We'll begin by writing down the classical wave equation that describes, say, a transverse wave on a string. And we'll remind ourselves of the solution. The displacement, y of x and t, and we note that a is the amplitude of the wave. Using this solution to the classical wave equation as inspiration, we'll say that a quantum mechanical particle is described by a wave function. To explain what the wave function really is very tricky, as different interpretations have different descriptions of what this wave function is and how it changes under certain situations. Mathematically, it is a complex object that contains all the information about a quantum mechanical system. We'll work with the example of an electron, and we'll say that it is just travelling in one direction, which we'll call the x-axis. This electron is going to be a free electron, meaning there's no potential. Let's work backwards then to try and get the wave equation for this quantum system based on a similar solution. Now let's recall some of the useful variables here. K is the wave number, and omega is the angular frequency. From energy conservation, we know that since the potential is equal to 0, the total energy of the electron is just its kinetic energy, which we can write in a more explicit way. We can also rewrite this in terms of the electron's momentum, and also again in terms of the wave number. This is due to the de Broglie relation, saying that every matter particle has a wavelength. Like the de Broglie hypothesis that describes matter particles having a wavelength, we can assume that the total energy of the electron is given by the expression for the energy of a photon, E equals hf. So we now have a new way of writing the energy conservation. We notice that the classical wave equation has a second derivative with respect to position. So we'll start to differentiate our proposed wave function solution to fit the form of the classical wave equation. When we differentiate once, we find a factor of k. When we differentiate again, we find a factor of minus k squared, multiplying our original wave function. Now, we have a factor of k squared, which is similar to the kinetic expression of the total energy. So let's rearrange this just to get the wave function on its own. We can now write an expression for the total energy times the wave function in terms of the second derivative with respect to position, like so. Let's try and find another expression for the total energy times the wave function in terms of the time derivative of the wave function, again following inspiration from the right-hand side of the classical wave equation. So we begin to differentiate with respect to time. We now have a factor of omega, which is similar to the expression for the total energy. But we can see that our function in the brackets isn't quite our original wave function solution as we would like. So we'll see if we can write this as some constant c times our original wave function. To find c, we can equate the coefficients. Let's look at the ones for sine and then cosine. After some manipulation, we find that c is just equal to minus I. So we can write the time derivative of the wave function in terms of our original wave function solution. Again, let's rearrange to just get the wave function on its own. So now we can write our second expression for the total energy times the wave function, this time in terms of the time derivative. And we can rewrite the other expression that we found for the total energy times the wave function in terms of the second derivative with respect to position. We now have two expressions for the total energy times the wave function, which we can set equal to one another, and get the quantum mechanical wave equation for this system. This is the one-dimensional Schrodinger equation for a free particle. We'll notice that this is just rewriting our statement for the total energy having to be equal to the kinetic energy for a free particle. Therefore, it's relatively easy to generalise to include a potential. We just rewrite the statement of the total energy equaling the kinetic plus potential energy. We can also generalise into 3 dimensions. Again, we note the conservation of energy, and we see that it is the kinetic term that changes. The kinetic term now has 3 components of the momentum. When we propagate this through, we find that that results in 3 terms of the second derivative with respect to each position coordinate. We can write this a little more compactly, using the operator del squared and using a vector position r. So now we can write the 3D Schrodinger equation.